Hello everyone, let's analyze. So today we're going to talk about sequence arithmetic. Specifically, if I have two sequences that converge, can I add them and get a convergent sequence? Can I multiply them and get a convergent sequence? Can I divide them and get a convergent sequence? And under what circumstances can I, if I can sometimes? So let's start with addition. Suppose AN is a sequence converging to A, and the sequence BN converges to B. Then if I form a sequence by adding element-wise the sequence entries of AN and the sequence entries of BN, then that sequence converges to A plus B. And so let's give a proof of that. Let epsilon be greater than 0. Right? It's in red because I'm done with my proof when I can show that the sequence AN plus BN satisfies the definition of convergence with a limit of A plus B. So that's exactly what my goal is. I need to show that there's a natural number n, and if little n is greater than or equal to that big N, then the distance between AN plus BN and A plus B is less than epsilon. And what is epsilon? It's an arbitrary positive number, okay? So once I can show that this statement here, my goal statement, is true, I'm done. So what do we know? It's always a good idea to begin with, what do you know to be true? Well, I know AN converges to A. What does that mean? That means there exists a natural number, we'll call it N1, such that if n is greater than or equal to n1, then the distance, that is the absolute value of the difference, between an and a is less than half of epsilon. Now, why half an epsilon? Why not epsilon? Well, really, I can put almost whatever I want here so long as what I want is positive. I can put any positive number, and for that positive number, there will exist a natural number. I'm picking epsilon over 2 in one sense, well, because I can, and in another, because hopefully when you saw this, you said, well, I feel a triangle inequality coming along. And in fact, if that's what you felt, your gut is correct. That's exactly where we're going. Right? We're going to have an AN minus A, we're going to have a BN minus B, a little triangle inequality action, and we'll get to our results. Similarly, since Bn converges to B, there's another natural number, we'll call it N2. And if n is greater than N2, then the distance between Bn and B is less than half an epsilon. Now let n be the larger of those two. Right? Meaning, if n is greater than this big N, then n is greater than N1, and n is greater than N2. Meaning, for this n, both this statement and this statement is true for this n, because this statement and this statement is true. Remember, if this, then this. Once this becomes true, the truth of this statement is in some sense activated. And again, notice the terms in red is every time I build a portion of my convergence definition. Right? So if little n is greater than or equal to big N, both of these inequality conditions are true. So, right, I began on the left with what I need to show less than epsilon. I began here. I rearrange, right, so my equality doesn't become an inequality because I'm just rearranging things. And now that I have this term and I can bound this term and this term, I'm going to apply my triangle inequality. This is less than epsilon over 2, and so is this. And I have my result. So let's go to our next arithmetic result. Again, let AN be a sequence converging to A and BN a sequence converging to B. Then the sequence AN times BN converges to AB. In other words, if I took my two sequences, which is just an infinite list of numbers, and multiply the entries of those sequence lists, right, entry by entry times each other, I'd build a different sequence, and that sequence converges to the product of the two limits. So before we get into the proof, let's do a little back of the envelope scratch work. All right, let's do a little figuring to see what exactly needs to be done to show that the sequence a and bn satisfies the definition of convergence with the limit of a times b. Now I know that because an converges to a and bn converges to b, then if n is large enough, right, if n is large enough, meaning there's some natural number out there for which I can make this less than whatever I want, or for whatever I want there's a natural number, and for whatever I want to fill in the blank here there's a natural number. So if n is large enough, I essentially have a blank check here, right? Because remember, the definition of convergence is that an gets arbitrarily close to a. The arbitrarily essentially means that I have a blank check. I can put any positive number here. I can put any positive number here. And if n is large enough, this inequality becomes true. So what am I going to fill it in with? Well, I'm going to fill it in with whatever I need to fill it in to get my result. Well, what do I need? Well, let's get working. I want to show that a and bn minus ab is less than epsilon, right, where epsilon is an arbitrary positive number. But I want to use this, which means I kind of have to separate, right? Here I have an a and b and an ab. I need to separate. I need to get that this is equal to, or it's less than equal to, something times an minus a and something times bn minus b. And then I can kind of fill in my blank check and put it to use. So the way I'm going to do that is by adding 0, but with style, which is I'm going to add a and b and subtract a and b. You see, now if I compare these two terms, I can factor out an an and I get bn minus b. That's as small as I like. If I compare these two terms, I can factor out a b and I get an minus a. That's also, well, as small as I like. So let me rearrange. So I took this term and this term, factored out an an. This term and this term, factored out a b. Now I can use my triangle inequality and the fact that I can factor out coefficients under an absolute value. So here I have an upper bound. How small is this? Well, as small as I need it to be. B is some number, so its absolute value is bounded by, well, some number. Now an is an arbitrary element of a sequence where n is large enough. What exactly is large enough? Well, that's to be decided. We'll get formal about the details. But again, this is just some scratch work on the back of an envelope somewhere. The question is, can I bound this for all n? Is the set of sequence values bounded? Well, we've proven that a convergent sequence is bounded, meaning there is a number that's greater than or equal to every sequence entry. And so if I take the absolute value of all sequence entries, then there's a number that bounds that. So let M be the maximum of the set of all sequence values of the absolute value of an and b. All right, so M is greater than or equal to, well, this should really be the absolute value of b. All right, so that should be the absolute value of b, my mistake. And this should be an. Now, of course, you know where I'm going. I want this to be less than epsilon over 2, and I want this to be epsilon over 2. So what do I have to fill in the blank to get what I want? Well, I fill in the blank with 1 over 2 times m. If I fill in the blank with 1 over 2 times m in both places, then my m cancels. I get half times epsilon. M cancels, half times epsilon. Half an epsilon plus half an epsilon, I get a full epsilon. And all I need is m to be greater than or equal to this and greater than or equal to this. And I know such an m exists because this is bounded and this is a single number. So I have in this scratch work everything I need now to put a formal proof. I know how close I need to make AN and A. I know how close I need to make BN and B. I know I can make them as close as I want, again, because convergence gives me this blank check of a bound. So I have everything I need to put together a rigorous, complete proof. Okay, so let's do that. Again, let epsilon be positive. Now again, in this slide, everything in red is every time I've accomplished something that shows the sequence A and Bn satisfies the definition of convergence to A times B. In the previous slide, I had all the A terms in red and all the B terms in blue because we were trying to separate them. So just to show you, right, the bright blue is all the B terms and the bright red is all the A terms, because our whole goal was to untangle these so that I get the B's together and the A's together, and then I cash my checks. Here, the red is showing that I'm making progress on satisfying the definition of convergence. Right? In other words, every time I make some headway on my goal statement there, right, which is just the definition of convergence for A and B and to AB, then I'm going to highlight it in red. Okay. Since AN converges, the set of the absolute value of the sequence entries is bounded. That means there is a number alpha that bounds the absolute value of AN for all n. So let M be the max of alpha or the absolute value in B. In the previous slide, there was a typo where I left off the absolute value. The fact that AN converges to A implies there's a natural number n1. And if n is greater than n1, then AN minus A is less than epsilon over 2m. You see, if I just led off with this slide, you might say, why did I say epsilon over 2m? Where did this come from? Right, but because we did the scratch work, we see why we had to choose this as our bound. And also notice the order that I'm giving the proof. Epsilon is defined as an arbitrary positive number. M is defined as some number that we're guaranteed to exist. And 2, well, we know what 2 is, right? So this bound is a well-defined bound, right? Which is why I needed to start with defining M and rationalizing its existence first. Since Bn converges to B, there's a natural number n2, and if n is greater than n2, then the distance between Bn and B is also less than epsilon over 2m. Then if n is greater than or equal to the max of n1 and n2, specifically meaning that n is greater than or equal to n1 and also n is greater than or equal to n2, then both of these inequalities can be put to use. They're both activated because both this statement and this statement is true. So A and Bn minus AB equals A and Bn plus A and B minus A and B minus AB. So all I did here is I added 0 so that I can disentangle my AN and my A's and my B's. So I rearrange them. This and this, factor out the AN, rearrange this and this, factor out the B. I utilize my triangle inequality. Notice for each of these proofs in the arithmetic, a triangle inequality is used. A triangle inequality is going to be a tool that we're going to use a lot in analysis. We know that AN is bounded above by M, so is the absolute value of B by definition. And that's less than or equal to M times epsilon over 2m plus m times epsilon over 2m, which is epsilon over 2, plus epsilon over 2, which is epsilon. So I've shown that my distance is less than epsilon. And I have my proof. And we know why we gave the bounds we did and why when we dropped them in, they just happened to work out so perfectly because of the scratch work we did ahead of time. Now, let an be a sequence converging to A and bn a sequence converging to B, where B is not 0, and that's important. We need B to be not 0. This statement doesn't work anymore if B is 0. Then the sequence an over bn converges to A divided by B. So a little back of the envelope scratch work. If n is large enough, an minus a is less than whatever I want, right? As long as what I want is positive. And bn minus b is also less than, right? Again, I have a blank check that I can fill with any positive number. So what do I need to put on that blank check to cover the cost of convergence? Well, I start with what I need to make small, right? I need to show that this converges to this, so I need this to be arbitrarily small. I need it to be less than an arbitrary positive number, which traditionally we call epsilon. Well, let's start by putting them over a common denominator. In order to separate it so that I get something that looks like this and something that looks like this, let's add 0 in the sense of adding AB and then subtracting AB. All right, then these two terms can be put together and I can factor out an A. These two terms can be put together and I can factor out a B. Now if I factor out a B, it'll cancel out that B there for that term. All right, so I have a and b minus ab over b and b. Again, this b, and this b will cancel. I have ab minus abn over b and b. I can factor out the a, and I'll just have a over b and b, but times b minus bn, right? Because that's where I want to get, because I can bound that by whatever I want. So here I let my b's cancel, and I get a 1 over bn. Here I factor out the a, b, and b, right? And then I separated this by using a triangle inequality. That's why I have a less than or equal to. Now here's where I have to pause before I can go on. I'm trying to show that this is as small as I want. Now here's the question. What's to stop bn from being as small as possible? Because if bn is arbitrarily small, then 1 over bn is arbitrarily large. And that's the opposite of what I want to do. I need to show that this is arbitrarily small, right? I mean, what if bn is as small as I want? What if bn is 0? That'd be terrible. I can't really go forward unless I can convince you that I need, or I can keep bn away from 0. Well, for n large enough, right? It could be that bn is 0 for some n. But I need to show that if I take n to be sufficiently large, then bn is well away from 0. And I can do that because bn is converging to b. It gets arbitrarily close to b, and b is not 0. So let's make a sketch. All right, since we're just doodling around on the back of an envelope, let's sketch this out. B is not 0. I can ensure that if n is large enough, bn falls in any positive neighborhood of b that I like. And so I'll pick b over 2. So if n is large enough, I can make sure that bn is between b minus b over 2, which is b over 2, and b plus b over 2, which is 3b over 2. This doesn't really matter. I just need to show that I'm away from 0. And In fact, if n is large enough, I can guarantee that I'm away from 0. Specifically, I'm to the right of b over 2. And the same is true if b is negative. If b is negative, if n is large enough, I can show that bn falls in any neighborhood I want of b. Specifically, I'm going to b plus b over 2, which would just be b over 2 if b is negative. And b minus b over 2, which would just be 3b over 2 again if b is negative. So if n is large enough, I'll fall within this limit. In other words, the absolute value of b minus bn is less than this distance, right, which is the absolute value of b divided by 2, right, whether b is positive or negative. So in both cases, I can guarantee that for n large enough, the absolute value of bn, in other words, the distance of this to 0, is greater than the distance of this to 0, right? So we can see that from our sketch. Of course, a sketch isn't sufficient. We have to show that it's true not just because of our sketch, but it's true intrinsically. So again, if n is large enough, bn minus b is less than any positive number. So I'm picking the absolute value of b over 2. Right? This inequality follows for n large enough because bn converges to b. Notice I wrote my inequality, usually bn minus b is on this side and the positive number bound is on this side. I did it reverse because I'm going to use a reverse triangle inequality, so I wrote it in reverse. Right? The reverse triangle inequality says this is bounded below by this. And remember, that's my goal. I need to show that bn is bounded below an absolute value. In other words, I need to show that it stays a positive distance away from 0. So that's why I'm using a reverse triangle inequality, so I can get that lower bound on the absolute value of bn. So that means this is less than this, using one of the results from my triangle inequality theorem. Right? Remember that triangle inequality theorem? I'm sorry, my absolute value theorem, where I had 4 different results. That implies that this is greater than the negative of this, the inside of this absolute value. Right? It's bounded above by this, and it's greater than the negative of this, which is what I have here. Now I add the absolute value of b to both sides, and I get that bn is greater than b over 2, which is what we observed in our sketch. Right, so we see that the distance from bn to 0 is greater than the distance of b over 2 to 0. Whether b is positive or negative, we get the same result. So because bn is bounded below an absolute value by the absolute value of b over 2, I get 1 over bn is bounded above by the absolute value of 2 over b. So I can bound this above, so it doesn't get arbitrarily small. Or rather, it doesn't get arbitrarily large. And so that's good if I'm trying to make this arbitrarily small. So now that I know that this is true, I can continue my work here. So I use the fact that 1 over bn, an absolute value, is less than the absolute value of 2 over b. Similarly, I use that same result here to get 2a over b squared. Now, remember, I can make this as small as I like. I can make this as small as I like. I've got a blank check because I know that convergence is true. What am I going to fill it in with? Well, I'm going to fill it in with something that's going to give me epsilon over 2 plus epsilon over 2, because that'll give me my epsilon, which is what I need. So I need to fill this in with absolute value of b so that this cancels, and a 4 so that this 2 over 4 becomes 1/2, this 1/2 here. There's an absolute value of a here, so I need to cancel that. B squared when b is non-zero is positive, so positive. These need to cancel, and again my 2, 4 cancels to give me a 1/2. So now I know exactly what to write into my checks. I've filled in the blanks. an minus a has to be this close, bn minus b has to be this close. Now, it also has to be this close in order to give me this result down here. So now that I have this back of the envelope scratch work, now I can put together a formal proof, right? Now I know how to slot and bound everything just right so that I get exactly the result that I need. So before we get to the formal proof, it is worthwhile for you to pause here and make sure that you go idea by idea and step by step, and make sure that you understand the ideas we were throwing around here before we put it together in a proper and complete proof. So let's do that. So here's our proof. Let epsilon be positive. Since an converges to a and bn to b, then there exists, well, n1, n2, and n3 such that if n is greater than n1, then an minus a is less than the absolute value of b times epsilon over 4. And again, if I just went straight to the proof, we might wonder, where in the world did this come from? Right? But now, because we did the scratch work, we know precisely where it came from. And if n is greater than n2, then bn minus b is less than b squared epsilon over 4 times the absolute value of a. Right? Again, it's a rather curious bound if we had no context, but we know exactly why we picked this bound now. And if n is greater than n3, then bn minus b is also less than the absolute value of b divided by 2. Now, if n is the maximum of n1, n2, and n3, and little n is greater than or equal to that maximum, specifically meaning that n is greater than n1, and n is greater than n2, and n is greater than n3, meaning all of these are true, meaning all of these inequalities are true. So if big N is defined to be this max and little n is greater than it, then the absolute value of b over 2 is greater than bn minus b, right? That's exactly this, right? This is true because little n is greater than n3. So this is true, right? I just wrote this greater than this, right? Because I'm trying to get that lower bound. So by the triangle equality, that's greater than or equal to the absolute value of the difference of the absolute values, which implies that the absolute value of bn minus the absolute value of b is bounded below by negative absolute value of b over 2. By adding the absolute value of b to both sides, here I get this expression, meaning 1 over bn is less than 2 over b, an absolute value of both sides. And now for the finale. I've got everything I need. So an over bn minus a over b. I put it over a common denominator. I add 0 just so. I separate the an and a terms and the b and bn terms because I can bound them, right? So I separate them in just the right way. I use the triangle inequality to separate them so that I can make use of my bounds. I factor out everything but the an minus a and the b minus bn. I use the fact that this is bounded above by 2 over the absolute value of b. I use that here and here to get this. And then I use the bound for this and the bound for this taken from these two steps to replace them here and here. That gives me this strict less than. Now, of course, we know that everything is going to factor in just the right and most beautiful way to give me epsilon over 2 plus epsilon over 2. Again, if I began with this page and skipped the back of the envelope scratch work, you might think I was a magician that just pulled these things out of a hat. But I didn't pull it out of a hat. I pulled it out of the back of an envelope. because, I did some figuring. Half an epsilon plus half an epsilon is a full epsilon. And I'm done because if I look at all the terms highlighted in red, I have satisfied precisely the definition of convergence of the sequence an over bn to the number a divided by b. And we're done. That's it for today.